Hello, everyone, and welcome back to Indian Genes. To all our listeners, first of all, a big thank you. We have just crossed approximately 500,000 listens on this podcast, and we have been rated as the number one science podcast in India by FeedSpot, a global podcast aggregator. And I think it's the support that we've got from each and every one of you. Today, we have an exclusive episode for you where we deep dive into a world that's never seen before on any podcast. That's because our guest today isn't just a scientist. She's one of the most original thinkers of our time. Professor Sara Seager holds the class of 1945 chair in physics at MIT and is also a professor of planetary science as well as aeronautics and astronauts. Her work on exoplanets, those planets orbiting stars beyond the sun, has reshaped how we search for life beyond Earth, from pioneering atmospheric detection to conceiving radical space missions. Her ideas stretch the boundaries of what we believe to be possible. You've likely heard of TESS, the mission that hunts down distant worlds. It was led in part by our guest today. Sara invited us into her MIT laboratory, and she guided us through the inner workings that you're probably going to see for the first time on any podcast of the Venus probe module. A piece of hardware never before shown on a podcast. It's kind of tech that lives in the intersection between theory and potential for detecting traces of life across vast distances. So prepare yourself for a conversation about ambition, creativity, and cosmic humility. Indian Genes proudly presents an exclusive conversation with none other than Sara Seager. So, Sara, from everyone here at Indian Genes and in India, thank you so much for coming back on our show. I know we spoke some time back, and it's been my fault. I've been trying to get you on back. We've had a lot of comments about trying to get you back, but I'm happy you spent some time now and we can be talking. So, for people who are probably meeting you for the first time, listening to you for the first time, why don't I let you talk, because I want to make most of the time that I have with you. So please tell us, Sara, what you do currently and everything that you want to tell us.
Great to be here. I'm Professor Sara Seager from MIT. Here, I'm an astrophysicist and planetary scientist, and I work on exoplanets, planets that orbit stars other than the sun. We're trying to study their atmospheres. Today, I'm here in my laboratory because recently I have added a new research subject area to my portfolio. And I've been slowly moving from astrophysics to, we could call it astrochemistry. And all of this is motivated by the planet Venus.
That's amazing. And I think there is a little bit of lag at the moment, but I'm going to keep going with the audio because I can get the audio. And I just want to get back to where it all started for you, Sara. And I was just thinking that 1994, if I'm wrong, if I'm right, was when it all started. And we probably did not know about exoplanets at that time. So thinking about students who are listening to us, or for you, the way I look at it, that was a risky move to get into exoplanets when nobody had thought that there were exoplanets. And how do you see that for you as a career, or you as a person, to making that blind leap into something that probably you believed?
Great question. Back when I started working on exoplanets 30 years ago, in mid-1990s, you're right. There were, at least when I got started, no exoplanets. And soon after, there were just a few. Well, one of the things was I was always a risk taker. I liked doing things, exploring. On the other hand, I was not committed to a career in astronomy. So I also had nothing to lose. Because when you're doing research, a large part of that is education, not just on the subject matter, but also on how to do research, how to be creative, how to problem solve, how to gain a skill like computer programming. So it was definitely a risk, and it really did pay off.
Right. And I see the probably, like you said, the current risk that in some people who are talking about exoplanets is when you talk about Venus. Now, I do know a lot of people would say that the possibility of life on Venus is pretty slim because probably in the clouds, it's the closest to us. Is that the reason why we want to try Venus first before we venture out? And what is your approach to this? Are you also thinking on those lines, or are you saying, let's tick this box out first? Or are you saying that there may be different forms of life that probably we are not yet ready to accept? And because of dogma about life on Earth, there could just
Yes, I
be
like
life out
that
there.
last
But
point. Yeah, I definitely like your last point. It's we're not ready to accept any kind of life in non-water solvents. Because the thing about Venus is, although the surface is too hot for life of any kind due to the massive greenhouse atmosphere on Venus, just like on Earth, when you go up a mountain or if you go in an airplane, it gets colder and colder. And on Venus, 50 kilometers above the surface, it's the right temperature for life. At 50 kilometers above, there's everything you need for life. There's energy from the sun, there's the right temperature, and there's liquid. The clouds are made of liquid, but they're not made of liquid water. They're made of concentrated sulfuric acid, which kills all of our own Earth life. So it is fair that people find it hard to believe that any life could survive in the Venus atmosphere. But there's two motivations. One is, why not look? Venus is accessible, it is next door, and nature is more clever than we are. Why wouldn't we want to go to Venus and take a look? Secondly, in my laboratory here that you can see all around me, we've been doing experiments in concentrated sulfuric acid to demonstrate, not that life survives, because our life does not survive, but to demonstrate that some complex biomolecules, simple and complex biomolecules, can survive in sulfuric acid.
right. And would that also mean when it comes to looking for these exoplanets, the biosignals that would go out because of sulfuric acid would be different from if somebody was looking down here towards Earth and they would be finding oxygen? So that in itself is, are we able to connect the dots as to what biosignal connects to what form of life?
That's a great question. And no, we're not able to connect the dots. Not yet, not right now. We are looking for gases that don't belong, that are produced in high. We wouldn't know what kind of life is making that. We cannot, create like an entire biochemistry, including metabolic byproducts. So that is a great question, but it's definitely for the far distant future. Where for Venus, we are talking not about looking for gases, but actually going to Venus to search for complex biomolecules, like solids, if you will, or liquids. Complex biomolecules dissolved in the cloud particles, to find molecules that are so complex that they aren't generated on their own without life.
Right. And these days, what we do know and what we do here when it comes to technology is in every field, as usual, there are different forms of analysis that are being conducted either through big data or through machine learning. Now, compared to what and when you started in 1994 to where we are 20, 25 years down the line, do you see the integration of AI with technology that we're talking about, for example, like machine learning? So instead of a particular person on a laptop doing it, do you think that you can use this help?
Well, we definitely use artificial intelligence in almost everything we do. And in astronomy, in exoplanet science, I have seen it more used. I mean, I consider two categories of AI. One is brute force. It's doing something you can do, it's doing an algorithm you could write, but it's just doing it more efficiently with less bias, with fewer mistakes. So that's one way to use AI. The other way to use AI, when it solves a problem or it can perform something we cannot think about. So it takes all the data, thinks through, not thinks, but it's learning on the data and it comes up with a result we couldn't have thought of. So usually in astronomy, the first one is what we do. We're using it to find exoplanets in our signals, to analyze exoplanet atmospheres, but it's not really putting things together in a new way. Now for Venus, it's very interesting, but for thinking about molecules and concentrated sulfuric acid and what we could look for and what life might be made of, believe it or not, it'll make sense when I say it, we don't have enough data for AI, because sulfuric acid chemistry, sulfuric acid organic chemistry, it's not a field. So we're taking our own data and we're thinking through like what we're going to do with that data. But we do see, not just in Venus astrochemistry, but in a lot of fields of science, the data's not there. So you have to embark on a program, not just like a 1 day or 1 week program. This is like a multi-year program to get the data you need to perform AI.
Right. And when you spoke about the possibility of life in sulfuric acid, for example, when it comes to Venus, or it could be Mars, or we do have places on Earth where there are primitive forms of life, very primitive, that may not emit biosignatures, but there is still life. And when we talk about Earth, we are emitting what we are emitting, but that does not mean there is no life still. If there is no...
Right, exactly. Like pick a place like in the desert or in rocks or like deep underground, there is life. And some of the life, it's very new, it's kind of starved for food, and it's just, we say, eking out an existence. Like this life, the cells might divide once a year. And so, yes, that life will have no signal we could see from afar with telescopes. But I love what you said, that the life is still there, even if we can't see it from far away. And when I think about the possibility for life in the Venus atmosphere, that's exactly what I'm thinking about. A very simple life form. It's just barely surviving, just kind of, barely getting by because it's so nutrient starved.
Right. And for people who are listening to you, I know that you're very deeply involved with TESS as well. And could you give us a little bit more about what TESS is exactly doing, and how does this tie into what we've just been speaking about to help us with these probably borderline areas?
Yes, I can talk to you about TESS. So switching back to exoplanets, one of the most prolific way, the easiest way at the present time we can find exoplanets is planets that transit their host stars. These are planets that are in a very special orbit where they're aligned just so from our viewpoint, the planet goes in front of the star as seen from our telescope. And so what we see is we see the stars, which are points of light, and we look at tens of thousands of stars at one time, looking for the rare cases when the planet is aligned so it goes in front of the star as seen from our telescope. And we see a tiny, tiny drop in brightness. And every time that planet orbits, whether the orbit is a day or a week or a month or a year, it will repeat that transit. TESS is a space telescope. It has 4 what I call glorified telephoto lenses. Each lens is basically forms a camera. So it has these 4 cameras, which are the big lenses with a detector at the bottom. And the lenses have a very large field of view on the sky. Each camera can contain an area equivalent to the constellation of Orion. And together, these 4 cameras, they work simultaneously, and they study a giant strip of the sky that is like 24 degrees by 90 degrees. And it stares at one field of the sky for about a month, and then moves over to an adjacent strip of the sky, etc., and tiles an entire hemisphere of the sky in 1 year. And TESS launched in 2018, and it's been operating ever since. So one thing about TESS is it's searching for transiting planets. So it's monitoring tens of thousands of stars, and actually up to millions of stars a month. And our computers search through that data, looking for the tiny telltale signature of a transiting planet. And a team here at MIT and elsewhere sorts through what the computer spits out and chooses planets we call TOIs, test objects of interest, which are planet candidates. And these candidates go on a list that goes out to the astronomy community, who do a lot of different follow-up observations using existing ground-based telescopes to confirm the planetary nature. So how is what we're talking about related to TESS? Well, our whole goal is to find planets that can support life, planets that are not too hot, not too cold, but the right temperature for life. But how it's related is, you know what? If we can really convince people or demonstrate that so many biomolecules of so many kinds are actually stable in concentrated sulfuric acid, this opens up a whole new range of planets we can call habitable. Because if a planet is warmer than Earth, the water may all evaporate and there will be no liquid water, but there could still be liquid concentrated sulfuric acid. So how it relates is that a lot of the planets TESS is finding, they're too warm to have water, but they might just be planets that could have liquid sulfuric acid, a liquid that might be a solvent for life.
Right. And I think from last count, and if I'm right, 638 was the number that TESS put out. And is this the number of planets that you call transitory planets currently on record?
Yes, and in fact, I'm not keeping exact track of how many, but that number sounds right. And those would be the TESS planets that are confirmed or validated as actual planets. But there are still a few thousand more planets. In fact, several thousand from TESS and the past Kepler and K2 missions that are waiting confirmation or validation. So yes, TESS has found so many planets. Its goal, TESS's original goal, was to find 50 confirmed planets. So TESS has exceeded its goals.
Wow. And I just want to come back to sulfuric acid, or did I miss that? Because when we talk about life and sulfuric acid for us here on Earth, we think of the possibility of destruction when it comes to sulfuric acid, and there should be no life next to sulfuric acid. But do we have proof that life can survive in sulfuric acid?
We have no proof life can survive in sulfuric acid. Well, let me tell you this. So our DNA is unstable in sulfuric acid, okay? Our DNA has a sugar phosphate background, and that sugar is destroyed in sulfuric acid. But what we're trying to do is we are trying to make an alternate DNA by swapping out parts, unstable parts for stable parts, so that I can share with you and the Indian Genes audience and the world that, hey, if we can find an informational polymer, a DNA-like molecule that's stable and folds in sulfuric acid, that of course won't say there's life there, but it will give us, it'll convince people it's worth searching for life there. So we have found, for example, our nucleic acid bases, so not DNA, but the latter part of the DNA, ACGT, stable for over a year in concentrated sulfuric acid. We have shown so far on our path to finding this DNA alternate that PNA, it's not DNA, but it's PNA, peptide nucleic acid. We've shown a single strand of peptide nucleic acid that has the same nucleic acid bases, but a different backbone, is stable in concentrated sulfuric acid at room temperature. We have a list of alternate bases. We have so many chemicals that are stable in concentrated sulfuric acid. Of course, a lot are not, but a lot of biochemicals are. We also have an experiment going showing that it's a little complicated to explain, but what people do in water people are trying to create life from scratch in water. And they take lipids, like a fatty molecule with a polar head, and they put it in water, and the polar head all points outward, and it makes a little tiny spherical vesicle, like maybe the first step towards the cell membrane. Well, we did the same experiment in concentrated sulfuric acid, and not only are these lipids stable, but they also form a tiny spherical vesicle. So we have like a growing list of things going on to show. I'm going to just show you a bit around my lab. I mean, there's a lot happening here, like so much, all experiments to show that molecules are, quantity doesn't equal quality, but we're doing a lot of experiments to show that things are stable in concentrated sulfuric acid. We have, a lot of things going on here in the lab, and we're doing a ton of experiments to work all of this out. And it takes a long time for things to make it out to the public, to other scientists. But we're slowly working on all these chemicals and trying to get them in like a digested format for people.
That's beautiful, and this is going to be cutting edge, right? If this sulfuric acid issue is sorted out, because I think you were mentioning earlier, we need to then change what we are looking for when it comes to life. It's still going to be life, but are
Well,
we ready for what we find?
well, we're not ready for what we find, and we are in a way still in denial. But would you like to see some mission hardware?
Oh, I would love to. I'm. This is an absolute pleasure to be doing this, and thank you so much. I'll switch to full
Okay.
screen.
So, what we're doing with all the laboratory work is we're trying to motivate missions to Venus. And my team, we call ourselves the Morning Star Missions to Venus. We have big plans. We have big plans to go to Venus with several missions. Now, our first mission is very simple, and we call it the Rocket Lab mission to Venus. So let me show you. This is a 3D printed version of the probe. So is well, actual size of the probe going to Venus. It's a small, relatively cheap mission, so there's no parachute. This is literally what's going to get dropped off by the Rocket Lab cruise vehicle at Venus. Our target launch date is 2026. Now, this it looks really small because it is small, but let me open it up for you. And inside is a pressure vessel. This is a 3D printed version of what will be inside, always stuck inside the probe. And the probe inside this pressure vessel, here's our antenna to communicate directly back to Earth. And our instrument will be in here. And the instrument will be shining through this window. The instrument's a laser. Well, we call our instrument an autofluorescence nephelometer. It will shine a laser through this sapphire window and through a hole in the probe. There'll be a hole here and it will shine out. It's going to hit about 20 centimeters outside. That's where its focal point is. And we'll be looking for autofluorescence. Autofluorescence will tell us that it's not pure concentrated sulfuric acid, but that there are some interesting organic molecules inside. Now here's a picture of the actual probe. And this picture is at NASA Ames, where NASA Ames has contributed our heat shield, and it's adhered. So that's the real one. And this is a 3D printed model. So that is our first mission to Venus. I'm going to show you a tiny bit of prototyping for our second mission. So our second mission will be far more ambitious. We want to send a balloon to Venus. And on that balloon, we will have a method to capture the cloud particles, to condense them, to evaporate the excess sulfuric acid, and then deliver what is left, hopefully, to our mass spectrometer. So when we do prototyping, it's kind of clunky to begin with. It's not intended to be anything that will go to space. It's just very clunky. So we have this thing here that's like a prototype for collecting clouds. And what it is, it's a series of wire mesh layers. So there's about 9 layers in here. And if you can go out into the fog or a cloud, the fog goes through here and it condenses on the metal mesh and shakes down, where it will come down here to where my hand is and drip into a tube. That's not what we're going to do on Venus, but that is what we've been testing. And here's a picture where we have taken it out to the environment, to a steam vent in Hawaii in this case, where it collected 8 milliliters of water in 1 hour. So once that material is collected, we are finishing off a prototype of what will happen to that liquid. Okay, sorry about that. Here is some more hardware. It's taken apart now, so I can't describe it in detail. But this is some prototyping for what happens after. We'll collect the liquid in a reservoir, and we'll be dropping it down onto some special tape that is sulfuric acid compatible. And that is some hardware for you to enjoy.
That's absolutely amazing. I think you've just made this video viral, Sarah, by showing us whatever you have, and probably the first time anyone has seen it live on a podcast. Thank you so much for that. And I just want to get back to the initial probe that you said, and you showed us the one that would land on Venus. How does that landing happen? Do you plan to, would it bounce in or would it get down on a parachute? And
No
how would you
landing.
protect that?
Remember, in our case, we're trying to change the way we do space science to have like a singular focus goal. So all we care about right now are the cloud layers of Venus. We're not trying to land. We're not trying to study the surface. So this probe will be, it's like throwing a rocket Venus. Okay, the probe is just going to come crashing, through the atmosphere. It will slow down due to its own drag. And it gets very, very hot below the cloud layers. So what will happen is the electronics will fail and it'll stop working. Now we have a pressure vessel, but as it goes down below the cloud layer, we're no longer going to be taking measurements. We'll continue to send data back to Earth as long as the probe is alive. But it'll keep going down. There's a small chance it's going to implode due to the high pressure, but most likely the entire thing will just crash land on the surface. And will it break? It might still stay intact, but by then it won't be working. And unfortunately, we will be littering. We'll just not really care about it, and it'll just stay there probably for a long time.
Very exciting. And like with landings, where a particular location is selected for a safe landing, when it comes to not a landing, like you said, the atmosphere, the cloud, would you all also be selecting any particular specific zone or area in the atmosphere of Venus that is more conducive to what you're doing?
That's a good question. In fact, our only real requirement is to go on the night side of Venus, not the day side, because we're trying to measure backscattered polarized radiation and autofluorescence. So we can't have contaminating light from our sunlight scattering through the clouds. So
Right.
we will have, Rocket Lab will choose a region for us, but our only scientific requirement is to go in the dark.
Right. And for all this amazing work that you're doing, Sarah, I can see that you guys are busy doing it. Now, what role does the private sector play? Because there's funding that's needed and you've got amazing plans, and I'm sure you're doing the best you can. But probably to get the voice out there to people who are interested in science, do you think that we need more active participation when it comes to the private sector? Because people talk about uh, mining in space, but this is equally important, if not more.
Well, the private sector is private because they're making a profit. And so it's not clear if their interests are best served by paying for a mission like this. Our first mission to Venus, we call it a public-private partnership. It turns out, though, that the search for signs of life or life itself on Venus, it's too crazy for large government agencies to support. So it's better aligned with private industry. We're trying to also invent, if you will, new ways to detect molecules, complex organic molecules, that we need to also have some overlap with Earth applications. And that's one way we try to hope to raise money to fund the instrumentation part. But for private funders, it's more likely, instead of being private industry, to be individual private donors. It's more likely to be, foundations that have money, that are philanthropically donating money. So that's kind of more where it's likely to come from. Another game plan would actually be to have the whole world participate. You could imagine ISRO being involved, India. We could imagine other countries that want to be interplanetary and do some cutting edge science joining together and supplying in kind, rocket launch, cruise vehicle. Other countries have come up, like South Korea. There's many other countries, Canada, that could play a role. So we have some plans. We're simultaneously trying to figure out how to get our next mission funded while also doing all the lab experiments to motivate those missions.
Right. And I know I have limited time with you, so I'm trying to bring in all the questions I can. But there are a lot of students listening to you, Sarah, and there's a huge community here in India, I think, that are space enthusiasts, and they look at you as a role model. Now, it is 2025, and if you look back at your journey, and what are the similarities to what you did in 1994, and to a young student out there who's probably trying to find their way through, what should I do? Should they pursue what they're good at, or should they pursue what's going to make a good living? And how does that balance together? What advice would that
Yeah,
be?
it is a great question. And the difference between me now and me 30 years ago is I have my own children now who are grown up. And so any young student out there, you're like my children's age. And as a parent now, I would answer, like, so when you're young, you'll say, just do what you love. And when you're older, you'll say, do something where you can earn money. So, your goal is to find something that overlaps. Find something you love doing that you're good at that also can earn a living for yourself. So one great thing about studying astronomy, studying math and physics, chemistry, is you can study it at school and it will lead to a job. The job may not be your primary desire, but with being trained in like the physical sciences, you will be employable somewhere. And that's something that I try to let people know about, try to hold on to. But one thing I've realized growing up and being older now is what is 50% equally important to your studies and learning is networking. Wow, I mean, who knew that that was so key? So that means getting out there, going outside your comfort zone, talking to people. It doesn't mean emailing me, okay? That is not going to help you. But it means finding a local university, attending the university, or if you're a high school student, going to talks, trying to meet real professors working at that university that could give you an opportunity. It means, depending on who you are, like if you have friends whose parents have any kind of job in tech, it means asking those parents for a summer job. If you don't have people like that, it's trying to find those people, going to college, trying to network with people at the college or alums of the college. So if I would have to give advice, it's find something you love doing that you're good at that also pays. And then hand in hand with that is the networking to try to get to the job that you love.
Right. And like the mission to Mars, I think you would summarize this by using the word perseverance, right? That's what's needed overall. And you mentioned earlier about growing up, and sometimes in the field that you are, with the innovation and technology and cutting ideas that you have to bring up, I don't even know whether growing up is a good idea, because at some time you've got to still stay curious. You've got to still have that, because sometimes we grow up too fast and then fall in line with everything that has been told to us.
Yeah, I really appreciate that. I want to underline that. And it's so important because once you do get a job, then you're consumed, your kind of mental capacity for the day, it's just consumed in the mundane. And it is very hard to be disciplined enough to save some me time, where me time could be at your work and being creative. So yes, it's very hard to keep that curiosity and to keep the joy of work alive.
Sure. I know we've gone about a minute over our time that you had given us. But before we let you go, Sara, once again, thank you so much for spending this time. It was amazing looking at your laboratory as well. And before we leave, we just hope we can do this again, probably when you have some more time. And we would love to probably have you or some of your students take us on a tour of everything you're doing. That would be amazing for people back home here. But any message for us before we let you go, Sara?
Thank you for your enthusiasm. I appreciate everyone loving space and continue to read about it and listen to podcasts. Thank you very much.
Thank you so much, Sara.